All right. Good morning again, everybody. I think we are now recording. So first, my apologies for not being able to meet you last Tuesday. Um, Sadly, my the brother of my grandfather passed away over the weekend, and last minute na nalaman ko na yung funeral niya ay kahapon. So and then I have lots of meetings yesterday which I cannot cancel. So napilitan ako na Tuesday bumiyahe papuntang Batangas para makadalaw man lang, and then kahapon ng madaling araw ako umuwi. So, kaya naabot ko yung 174, pero nawalan naman ako ng internet para dun sa 151. So, sorry din sa mga nagwa-151. Tapos nakapagklase na uli ako nung 5:30 to 7 kahapon. Pero yun, that's why I was not able to meet you last Tuesday. But I hope you use the time to talk again with your group mates to work about problem set 1.1, or at least plan what's the division of labor, kung paano nyo isosolve yung mga problems na nandun, and if you encountered some difficulties, all right? So, but any updates or any questions about the problem set? Kailan nga ba deadline nun? I forgot when the deadline is. Tandaan niyo ba? Or kinalimutan niyo talaga? Sabi ni Neil ay October 21. Bakit ang haba? Ang haba nung deadline. Parang na-hypnotize ako nung sinet ko yung deadline na yun. Bakit October 21? Kaya pala medyo matagal-tagal pa, no? Kaya siguro hindi nyo pa iniisip. So October 21st yung deadline. All right. But there's a second part to the problem set. Ipapatry ko sa inyo namang padamihin yung number of points. So siguro ibibigay ko na lang next week, tapos yung deadline niya ay after the reading break. Probably 1 or 2 weeks after the reading break. Pero ibibigay ko na ng maaga. Bibigay ko within the week yung part 2 para masilimulan nyo na rin gawin. At maplano nyo yung mga gagawin niyo sa mga susunod na panahon. Pero yeah, mahaba naman pala yung time na binigay ko. So if you haven't found any groupmate yet and you're looking for a groupmate, so kindly send me a message. Hindi ko alam kung open pa yung Google Doc. Hindi ko pa uli siya nabisita right after the deadline. Because if I remember it right, I gave you a deadline to fill up the Google form or the Google Doc. Tapos yung mga nakasubmit before the deadline at nagsabi na gusto nila mag-work with somebody in the class, kaya lang hindi nila kakilala kung sino pa yung mga walang ka-group, pinair ko na sila or inihanap ko na sila ng mga groupmates. So for those na mga wala pang ka-group that are looking for someone to work the project with, sabihan nyo na lang ako, right? Send me a PM or send me an email, tapos i-group ko na lang kayo, right? Kaya pala hindi pa kayo nagpapanik kasi October 21 pa, and I guess dahil October 21 pa, wala pa kayong questions, ano? Pero just let me know. Kasi this is an open problem actually because I haven't tried it. Hindi ko pa tinry ko ano yung nangyari kapag si A ay 0.0, pag mas maliit siya kay 0.04 or mas mataas. Nakita ko na yung resulta ng convolution. Alam ko yung mangyayari sa convolution ni F pag mas malaki yung A or mas maliit yung A. Ang hindi ko lang sure, kasi hindi ko pa siya ni-run, ay ano yung mangyayari dun sa pagsosolve ng inverse problem. Kung meaningful pa rin yung result or hindi. Because varying the value of A will definitely have an effect on how the convolution will look like. And I don't know if 64 points will be enough to capture that behavior. So there is a possibility na hindi maging maganda yung reconstruction nyo kay F. Kasi baka nung binago natin si A, either nung pinaliit natin siya or pinalaki, baka hindi na enough yung 64 points dun sa discretization. Pero ngayon, ang pinagawa ko pa lang sa inyo sa problem set 1.1 ay baguhin si A. Babaguhin si A, mababago si nu. So yung number ng non-zero entries dun sa coefficient matrix A ay hindi na magiging 5. Either dadami yun or liliit, depende dun sa mahanap nyo na nu. So kailangan yung i-reconstruct yung matrix A na circulant. I think circulant pa rin siya, kaya lang mababago na kung ilan yung non-zero entries per row. Right? And it's an open problem because I don't know the exact answer kung ano yung mangyayari dun sa reconstruction. So just feel free to update me kung may preliminary results kayo because I'm really interested to see what will happen. Kasi yung susunod na part ng problem set 1, yung problem set 1.2 ay ipapano ko naman, papadamihin natin yung number of points. Instead of 64 points from 0 to 1, gagawin naman natin halimbawa 128. titingnan natin kung ano yung mangyayari. And of course, you need to make necessary adjustments dun sa code. Pero don't worry, siguro ibibigay ko yung problem within the week or over the weekend. Tapos, ang deadline naman niya probably is 2 weeks after the reading break. Tapos kayo na rin yung magkaka-group para sabay-sabay yung binabago yung code. All right? I think that's the housekeeping matter that we'll have. Sorry, kailangan ko mag-on and off ng mic from time to time kasi yung, alam niyo na, yung runny nose or, hindi ko alam, runny nose or pag mayaman daw kasi ang tawag dito, ayan allergic rhinitis. So, hindi ko alam, umatake siya pag nagklaklase ako. Pero kanina nung nagmi-meeting ako, wala naman, di siya umatake. Nakapagsalita ako without any pause, without my runny nose affecting me. Pero ngayon, eto na, nagkaklase na. All right. So anyway, so for today, we'll start talking about another inverse problem. Medyo iba naman yung approach because in the convolution problem, ang ginawa natin ay tiningnan natin kung paano mag-translate ng isang a continuous operator. The continuous operator is the convolution operator, which is basically an integral. All right. So essentially, ang ginawa natin before, we are computing the operatorial equation AF equals G. All right. Ito yung given. And then we are dealing with the inverse problem. So basically, G is given to us. Alam natin yung output function G, and we're trying to reconstruct the output F, right? And basically, this operatorial equation, by definition, is the integral from negative a to a ng psi of y times f of x minus y. And then the integration happens with respect to y. Okay? And then this is equal to the function g. Natin, sorry, I was cut off there. Pinag-aralan natin kung paano i-discretize itong operatorial equation na to. And it's not just an operatorial equation, it is actually an integral operator, right? Or it is an integral equation na hindi natin dinidiscuss in any course dito sa undergrad BS sa BS Math, ano. Ang meron tayong background ay how to solve ordinary differential equations, yun nga yung nasa 151 or PDEs na nasa 152 and so on. Kaya don't worry kung medyo nahirapan kayong sumabay when we are dealing with the integral equation because you don't have enough background about integral equations, and I learned na yung iba pala sa inyo ay hindi pa nag-120, so siguro medyo na-lost din kayo when we talk about the discretization kasi naging matrix equation yung wino-work natin. But hopefully you kind of adjusted na. So today we'll be talking another type of inverse problem. Pero alam nyo na, kapag nagdi-discuss tayo about inverse problems, we can't help but to study the forward problem first. Because as we have mentioned in the introductory sessions, that a meaningful discussion about inverse problems will require us to get a good understanding of how the forward problem works or how it is solved, right? So kasi nga ini-inverse lang natin yung process o ini-invert lang natin yung process para ma-solve yung inverse problem. So kailangan nating pag-aralan kung ano yung nangyayari dun sa forward problem. Okay? So for today, we'll talk about the heat equation or heat propagation. Now, this is section propagation. So this is basically, I think, chapter 2 or section 2, 2.1 and 2.2 in Siltanen's book. Did you get or do you have access to the book of Siltanen? Nakahanap ba kayo ng kopya? Because if not, I can share with you some snippets or some excerpts from the book. I think magiging ano naman siya, exempt under copyright law kasi ano naman tayo. We did the class tapos hindi naman buong material yung i-share ko sa inyo. So wag niyo lang siyang i-share outside, ano. So I'll give you some excerpts. Kaya lang yung chapter 2.1 niya ay medyo technical yung discussion. Today I'll try to discuss 2.1 in Siltanen's book, pero just a little bit of physics. Hindi ko dadaanan yung probability or yung stochastic process that is involved in the heat propagation. Okay? So kasi dito, pag-aaralan natin kung paano nagtra-travel or nagpro-propagate yung heat in a tin rod. Okay? Tapos titingnan natin ano yung mga inverse problems na pwede nating isolve involving the heat equation and how to discretize the resulting model. Kasi magkakaroon tayo dito ng isang PDE, isang partial differential equation, and of course, our goal is to have it solved using computers. Madali lang sana yung inverse problem isolve analytically, pero kailangan natin yung mga tools mula sa Math 152, paano mag-solve ng isang PDE. Pero yung mga nakapag 152 na dyan, or kahit yung mga nag-151 or nag-151, alam nyo na hindi lahat ng PDE at hindi lahat ng ODEs ay madaling isolve. Alright? Kung nag-151 kayo ngayon, you see na nakadepende dun sa forma o sa itsura ng ODE yung solutions na pwede nating isolve. So napaka-limited ng mga hand techniques natin on how to solve this differential equations na kapag ka meron siyang isang kakaibang form, baka hindi natin siya kayang isolve analytically. All right? That's why we always go to a discretization of a PDE. And that's what we'll talk about. So the discussion that we'll have on the heat equation will be divided into probably two phases, okay? Or actually kahit three phases. Number one, I'll give a short introduction on how we derive the heat equation. Second, ay titingnan natin yung titingnan tayo ng isang example. Paano hindi naman paano mag-solve, pero pag-verify ng solution sa isang forward problem. And plus, titingnan natin ano yung setup kung gusto nating i-discretize yung solution sa heat equation. Alright? So again, we'll have a continuous operator. This time, hindi siya integral equation katulad ng convolution. Ang continuous model natin dito ay isang PDE. And then we'll ask the question, how do we translate this continuous model, which is a partial differential equation, into more of a discrete model? Meaning magiging linear system na rin siya. And this is fine because the differential operator, so in general, yung pagdi-differentiate or pagkuha ng partial derivatives ay isang linear process, right? Meron siyang linearity property. The sum of derivatives is the derivative of the sum. And then the derivative of a scalar product is the scalar product of the derivative. Okay? So kaya meron siyang linearity property. Gusto natin talaga itong mga linear inverse problems kasi nga kaya natin siyang ibaba mula sa isang continuous problem papunta sa isang linear system. Okay? So ito yung isang example. So let's dig into discussing how the heat equation came about, right? So for simplicity, as in the modeling of physical systems, nagsisimula tayo sa isang actual scenario, isang actual problem, right? So we will be tackling how do we model the propagation of heat or the heat flow in a domain, right? So parang halimbawa nasa bahay ka, nasa isa kang room, right? So gawin natin nasa cube ka, right? So halimbawa yun yung kwarto mo, sige, lagyan pa natin ng roof para kunwari nasa bahay ka talaga. So it is very interesting to see that how heat will propagate, right? And then there are several factors that will affect the heat flow, right? So halimbawa meron kang aircon dyan, tapos it gives cool air, right? Kaya lang, merong mga outside factors like the heat outside. So, halimbawa, nandyan yung araw, parang sunny side up. Pero sun yan, walang kokontra. So, merong energy from the sun that will try to affect or that will affect how the temperature in the interior of the earth will be, right? Tapos, syempre, makaka-apekto yan kasi uh, may material composition yung walls, pero depending dun sa material composition ng wall mo, yung ambient temperature outside will have an effect on the temperature inside. So ang titingnan natin ay with all of this different properties or this different components of this physical phenomenon, we want to know how does temperature change inside of our domain. So titingnan natin halimbawa, what is the temperature at this particular point, okay? So titingin tayo ng point. So in 3D space tayo, no? So we will denote the temperature by the function u. And we'll ask, what is the temperature? That means what is the function value of a function u, the temperature function, at the particular point given, or the particular point of interest, or the point of observation. Let's have x, y, z as our spatial variables. So sila yung mga spatial variables kasi sila yung nakadepende dun sa space, right? But we know that heat propagation is not just dependent on the spatial variables, pero meron din tong time component. Kasi dynamic in time yung heat flow, right? So yung temperature ngayon in a particular scenario, in a particular time will be different from the temperature 5 minutes from now. So kaya ang daming variable. Meron kang dalawang klase ng variables kay U. So yung temperature is determined by the spatial variables. Depende kung nasa ang dimension ka. And then there's a temporal variable, which is basically our time variable. Okay, so kaya dalawa yung klase ng mga variables na nandito, spatial and temporal variables. Kaya naman, partial differential equations yung titingnan natin dito. Hindi siya ODE kasi para maging ODE, isa lang dapat yung variable. Right? Tapos natutunan nyo sa 38 sa multivariate calculus na magkakaroon ka na ng partial derivatives kapag ka more than one variable na yung involved. Right? Oh, before I go any further, may I see a show of hands kung sino yung mga tapos na, sino yung mga nakapag 152? Okay, so walang nakapag 152. Don't worry, wala namang quiz or hindi ko naman kayo pagdidiskitahan pag na-take nyo na yung courses. Ano. Si Jane. Jane, nakapag 152 ka? No, math 152. So math 152 is partial differential equations. So wala. So mahirapan akong i-discuss itong heat equation. And this is one reason why kung mapapansin nyo, wala pa akong write-up, wala pa akong handout about this section because I don't know how deep should my discussion be kasi nakadepende siya dun sa background nyo. So wala pa nakakapag-PDE. So I'll try to be as basic as possible in this discussion. And then sino yung nakapag 151 na? Yung tapos na sa 151? Wala pa rin tapos sa 151? O ayan, tapos na si Jay, si Denmark. Okay, si Jane. And then the rest ay nag-151 ngayon. No? Si Daryl, tapos na rin. Okay, good. And then the rest ay nag-151 pa lang. Okay. All right. Okay. Sige. Tapos, yeah, I think that's fine. So I'll try to be as as simple as possible, ano? And then if there are some technical terms that I'll use na hindi kayo familiar, just call my attention, raise your hand, and then or give it a chat, ano? Give me a chat. All right. So ito yung model, pero ito ay nasa 3D na. Ito yung usual thing. If you're doing mathematical modeling, kahit sa physics, kahit sa engineering, ano, meron isang problem that is basically motivated by a real life application. So basically here, temperature flow in a room, right? So yung forward problem, alam mo yung mga information about the heat source, information about the material composition, about your geometry. So basically, parang pag i-model ko to sa PD, alam ko yung mga boundary conditions. Alam ko yung ano yung temperature sa mga walls ng bahay. Alright? So yung temperature dun sa wall is basically influenced by the energy from the sun, the greenhouse effect dito sa ating environment. So basically, all of them can boil down into boundary conditions. Sila yung nakakaapekto doon sa doon sa temperature, doon sa boundaries ng room. So basically, in this case, the boundary conditions will be given by the temperature at the walls and at the roof. So yun yung mga magiging boundary conditions. So kumbaga sa ODE, ito yung mga parang initial conditions. Ano yung mga alam mong ano yung mga conditions na alam mo na nasa-satisfy ng solution. Kasi kung wala kang ibibigay na boundary o initial condition, you will have an infinite family of solutions, right? Meron kang general solution. Yung may mga parameters pa na C, o kaya D, o kaya K dun sa solution ng ODE. Right? So para magkaroon ka ng specific function na solution, kailangan mo magbigay ng initial condition. So you will have a PDE telling us how U behaves in terms of derivatives. Tapos meron kang boundary condition so that you know the temperature U doon sa loob ng room. But that is the forward problem. So you have a governing principle, you have a governing law, which is a partial differential equation involving the function U. Alright? Merong mga derivatives si U with respect to the spatial variables. May partial derivative siya with respect to the temporal variables. Tapos i-derive natin ano yung relationship sila para makuha yung governing law. The governing law will be a PDE. Okay? And then if you want to know the forward problem, to solve the forward problem would be finding the temperature at a particular point in the room and at a particular time. So kailangan mo makuha ano yung itsura ni U as a function of the spatial and the temporal variables. And that solution will depend on the boundary conditions. So once we have established the governing law, alam na natin yung PDE, tapos alam na natin yung initial conditions, then we can use tools or techniques that you have learned or you will learn in PDEs para ma-solve yung function U. Yun yung forward problem. Alam natin yung boundary conditions. Gusto kong ma-predict ano yung temperature dun sa loob ng room at a particular point in time. That's a forward problem. Now, the inverse problem, may dalawang klase ng inverse problem, alright? The first inverse problem ay parang unknown yung boundary conditions, right? So you have a desired temperature profile or a temperature distribution inside the room. So meron ka nang alam na function U. Halimbawa, gusto mo sa room mo equal lang yung temperature lagi kay 25 degrees Celsius for all time and for all points inside the room. So the question is, what should be the input in your aircon? So ano dapat yung behavior ng ating heat source, naka-quote unquote yung source kasi nga hindi siya heat source kasi siya yung magbubuga ng malamig na hangin. Siya yung magbibigay sa atin ng mas mababang temperature. So how hard, or the question in the inverse problem is, how hard should the air conditioning unit work to maintain a temperature, a desired temperature profile inside the room? Of course, you still have your boundary conditions, alam mo yung temperature sa labas, paano siya nakaka-apekto dun sa temperature dun sa loob, right? So, kailangan mo malaman paano dapat nag-work yung heat source, which is your air conditioning unit, to basically control or maintain a desired temperature inside the room. Okay? Now, you could make a fancier inverse problem by saying, okay, hindi lang yung heat source yung i-control ko. Gusto ko ring i-control yung temperature dun sa boundary. Alright? Which is, hindi pa ganun ka-realistic, pero pwede mong tingnan, ano dapat yung boundary condition? So, ano dapat yung temperature doon sa mga walls at saka dun sa roof ng bahay para ma-maintain ko yung isang desired temperature. Kasi nga yung boundary conditions, pwede mong tingnan as an input to a problem. In this physical scenario, dito sa typical air conditioning problem, wala tayong control dun sa boundary conditions. Kasi hindi natin alam or hindi natin nakokontrol yung temperature dun sa walls. Unless meron kang high-tech na aircon na kaya niyang baguhin yung temperature ng isang concrete wall. Halimbawa, nag-one piece dyan, so kung nasa Egghead Island ka, meron kang isang island-wide na air conditioning unit na kaya mong gawing tropical yung temperature dun sa loob ng isang winter island, So, yun na yung high-tech. Kaya mong i-control yung temperature dun sa boundaries. Pero of course, we don't have any access to that. So, yung heat source lang yung kaya nating i-control. So basically, how should the air conditioning unit behave so that we can maintain a desired temperature U? Halimbawa, U equals 25. So that's going to be our inverse problem kasi alam mo yung output. Alam natin yung desired temperature flow. Ang tinatanong natin ay paano ko siya ma-achieve? Paano dapat nag-work yung air conditioning unit o yung heat source? Okay? Now, another inverse problem, which is much easier. Ito yung diniscuss ni Siltanen dun sa section 2.2 niya ay, halimbawa, alam ko yung temperature at a time t. So we know halimbawa, known yung U, X, Y, Z, comma capital T. So we know the temperature, or we know the terminal temperature. So T is a given time value. Halimbawa, alam ko yung temperature inside the room, at all points inside the room at a particular time, capital T. Now, we pose the question or the inverse problem of what was the temperature distribution in a time prior to the terminal time big T, right? So gusto ko mahanap yung temperature profile. Okay, so I want to know what the function u in terms of x, y, z, and little t for all t that is less than capital T. You can think of it still as an inverse problem kasi alam mo yung terminal temperature. Alam mo yung temperature at a particular time capital T. And the question is, what is or what was the temperature prior to T? Right? Inverse problem pa rin siya kasi makikita natin later na yung temperature at time T will depend on prior temperatures. So parang ang output pa rin, nung makikita yung proseso rito, especially when we start discretizing the heat equation, ay yung temperature sa time T plus 1 ay nakadepende sa temperature ng time T. So kaya pwede mong tingnan yung temperature at time capital T sa terminal time, siya yung output ng forward process. Alright? So alam mo yung temperature ngayon, malalaman mo using that kung ano yung temperature in time capital T. Now, the inverse problem is baliktad naman. Alam ko ngayon yung temperature sa capital T or time capital T. Gusto kong malaman ano yung history ng temperature distribution. Alright? Kaya dito ay time less than T. Although you might think wala siyang masyadong practical applications kasi na-experience mo na yung heat na-experience mo na yung temperature at time little t. Bakit mo pa siya isosolve? Well, if you're doing data mining or historical, or if you want to get a historical profile, kailangan mo malaman ano yung prior temperature. Okay? Though hindi siya masyadong aligned dun sa introductory example ko kanina. Okay? So that's the phenomenon that we want to look at here. Pero of course, ang daming physics na involved, ang daming modeling na involved, lalo na kung multiple dimensions yung gagawin natin. So we will do what mathematicians do best. Lagi nating sinisimulan sa zero order approximation, yung modeling. Kasi kailangan nating maintindihan, kailangan nating matutunan kung ano yung governing principle. At ang ginagawa sa math, ano na rin, parang research sharing na rin, no? Lagi tayo nag-start dun sa zero order model. Kahit sa physics pag-aaralan nyo muna kung ano yung mangyayari sa pinaka-simpleng scenario. And then we do the math on this simple scenario, bibuild natin yung theory, paano siya sinusolve, tapos ang susunod na step ng research ay paano ko siya may extend into multiple dimensions. Paano ko may add yung physical assumptions from the physical phenomenon na pagka sinama ko siya kagad sa modeling, napakahirap ng intindihin ng process. So mag-start ka sa simple, tapos saka mo dagdagan yung assumptions o yung mga conditions para maging realistic siya and so on and so forth. Alright? So parang ano to, bago pa to sa prototype stage. So simple muna, ipakita muna yung proof of concept bago ka gumawa ng prototype. Kasi pag gagawa ka na ng prototype, dapat dapat na factor in mo na yung mga physical conditions that will make basically the modeling very tedious, especially at the beginning. Okay? And with that in mind, yung three-dimensional problem natin kanina ay ipapalitin ko na sa isang one-dimensional problem. Okay, so instead of tackling the heat flow problem in three-dimensional space, titingnan ko muna in one dimension. So I'll consider a model, a very thin rod. Titingnan natin paano nagpro-propagate yung heat dito sa very thin rod na ito. So basically, you have a very thin rod, tapos we have here, tawagin natin itong 0, tapos ito si capital L. So one dimension lang, isa lang yung temporal variable natin. So we want to know how heat propagates at this on this rod, on this very thin rod or very thin pipe. Kailangan ko yung term na very thin para maging one dimension na lang siya. Kasi pag meron kang isang rod o isang duct, so two-dimensional pa rin yan. Actually, pwedeng maging three-dimensional pa rin Pero just to justify the simple modeling now, I'll consider a very thin rod para masabi na wala siyang width, maliit lang yung width, maliit lang yung height. So basically, ang nagma-matter lang ay yung length. And we will consider a finite length rod. So isa lang siyang rod where the temporal variable x runs from 0 to L. So sorry, not temporal, yung spatial variable. So isa na lang yung space variable natin, si x na lang. And x is an element of 0 to L. Okay? So the question here is, what is u of x comma t? All right? Where x is an element of the interval 0 L, 0 to capital L. So temperature, yung uxt. So paano nagva-vary yung temperature all throughout the rod? So x goes from 0 to capital L, and t is a positive number which represents the temporal variable. Okay? So gusto nating malaman paano nagbe-behave yung function u, right, which represents the temperature on this very thin finite rod starting from x equals 0 until x equals L at particular times starting from 0 to positive infinity or from 0 to capital T, kung finite lang din naman yung time variable na i-consider natin. Okay? So ito yung idea. Okay. So let's try to build up the model for the heat flow. All right? So ano ang gusto nating makita, kasi sabi ko kanina, in-spoil ko na, si U laging determined yan by a PDE. So kailangan ko makita yung rate at which the temperature change. So rate at which the temperature change at a particular point x in space and a particular moment in time t. All right? So sige, let's think a little bit. Let's imagine the scenario. So ano ba yung nakakaapekto dun sa temperature flow or sa rate of the rate at which the temperature changes? Sige nga. Ano yung mga factors? Hindi nyo kailangan ng physics, ano lang, layman's terms or imagination, common sense. Ano yung mga nakakaapekto dun sa pagbabago ng temperature? Do you have some ideas? Kunwari, wala pang mga laws of thermodynamics, So, kunwari, nire-rediscover natin yung ginawa para ma-appreciate nyo kung paano nagmo-model, Victor is saying the material. Yeah, that's good. Yung material ng rod. Kasi kung good heat conductor yung rod, dapat naka-incorporate yun dun sa model. Alright? Kung siya ay hindi siya magandang heat conductor, then it should be part of the model. So I'll just take note of that. So kailangan dapat itong right-hand side natin, this should involve the material, all right? Or it should involve some quantities related to the material. O siguro dapat nating i-consider yung material composition. So, mamaya natin siya i-quantify. So, puro verbal lang, puro qualitative lang. Ano yung mga bagay na pwedeng makaapekto dun sa propagation ng heat dito sa rod? So, meron ng isa. Thank you, Victor. Yung material. Yung properties ng material. What else? Okay, Neo said heat from the environment. Yeah, that's correct. Pwede ko siyang sabihin na, okay, heat source, right? So sabihin ko na lang siya ay heat source. Para mas general, So yung heat source, pwedeng siya yung ambient temperature from the environment, okay? So dun sa example natin sa bahay kanina, depende kung anong temperature sa labas, syempre nakaka-apekto yun dun sa temperature sa loob ng room kahit meron ka ng aircon, right? So halimbawa, mainit sa labas, so your air conditioning unit should work harder just to maintain the desired temperature. All right? So that's okay. So pagsasamahin ko na dito, kasama na rin dyan sa heat source, ba yung aircon or ano yung nangyayari dun sa boundaries. Okay? And then ano pa? Ano pa yung nakaka-apekto? So heat source, material composition, what else? Yun lang ba yung nakaka-apekto? Actually, may isa pa. Pero parang ano siya, parang napaka-implicit dun sa model and we take them for granted. Sige. Size of the object, yes, pero Victor, doon ko na siya isasama sa material properties, ano. So yung object o yung size ng thin wire, dito na natin siya ifa-factor in sa material composition. Okay? But that's right. Depende dun sa laki ng environment, no. Yeah, sa laki ng environment ng object. Any other guesses or any other ideas? Na-miss ko yung ganitong klase habang nag-iisip kayo, no, on the side. Kasi parang nitong sa pandemic, ano, lalo na nung bumalik ako dito sa LB, parang ano, parang nakatali na kami dun sa prepared na slides o dun sa prepared na modules. Parang nawala na yung parang spontaneity ng lectures. Na-miss ko yung ganito na ginagawa ko lang siya sa Blackboard, etc. Pero feeling ko ngayon pwede na natin gawin, no? Kasi lahat naman ay required na kayong umattend ng synchronous classes, no? So, yeah. Okay, what else? Medyo technical nga siya pag inisip mo, no? Okay, so, yung change in the temperature ay of course naapektuhan ng heat source, right? But we also need to account the very nature of the flow of heat within the material or within the object, right? Kasi kung meron kang heat source halimbawa dito sa boundaries, so meron ditong heat source, so nag-apply ka dyan ng heat, nag-apply ka dyan ng heat, alright? So aside from the material composition of the object, syempre, etong heat na in-apply mo sa boundaries, it will have some, according to some behavior, magpropagate yung heat dito sa loob ng object. Alright? So kailangan nating tingnan kung paano na-diffuse yung heat or paano siya na-distribute. Paano nagflow yung heat from one point to another. And that's what the bulk of the model should talk about. Of course, aside from the heat source, kasi doon manggagaling yung propagation ng heat. Of course, aside from the material composition, pero there's an inherent uh, what you call this? There's an inherent phenomenon that governs how will heat flow inside of any material. And basically, pwede natin siyang tawagin na heat diffusion or heat flow. So how heat flows within the material. So pwede nating i-add itong dalawa. So meron kang heat source, pero kailangan nating malaman or i-quantify paano travel yung heat from one point to another. Because we will assume here that we only have access at points x equals 0 and x equals L. Kasi sila lang yung boundary. So ito yung parang boundary conditions dun sa ODE o dun sa PDE. So mag-apply ka dito ng heat, mag-apply ka dyan ng heat, pero hindi lang dun sa heat na in-apply natin, nagdedepende yung behavior ng temperature. Pero we need to ask, how does heat propagate within a medium? Paano nagta-travel yung heat mula sa point 0 at sa point L inside the interior of the rod? So ito yung tinatawag natin na heat diffusion. Okay? Or heat flow. Mas maganda yung heat flow, no? Mas laymanized. Paano nagfo-flow yung heat? Kasi pag may heat source ka dito sa magkabilang dulo, hindi lang naman dyan naninirahan yung heat. Due to the very nature of heat, magpropagate yan dun sa interior. Quantify dito aside from heat sources. Okay? So I hope that makes sense. Question. Paano ngayon ano yung behavior ng heat? Bakit nagfo-flow yung heat? O ano yung nagko-cause ng change in temperature due to heat flow? Sige nga, sinong mga magagaling sa physics dito? Ano yung nagko-cause ng heat na nagko-cause ng change in temperature? Sabi niya, sir, kaya nga hindi ako nag-physics eh. Ayoko na mga ganyan-ganyan. Pero nag-ano kayo, no? May physics subject kayo. Inabot niyo pa ba ang thermodynamics or something like that? Ano yung nagko-cause ng pag-travel ng heat? Or ano yung nagko-cause ng heat in general? No idea? Sige, kahit hula. Wala namang bayad yung hula, eh, 'no? Saan nanggagaling yung heat? From a physical point of view. Sirit na? So basically, we experience heat dahil dun sa pagkikiskisan ng mga molecules in the air or in the medium, right? So you excite the endpoints of a material or of a particular object in space, ano? So mag-apply ka dyan ng heat. You apply heat by forcing molecules to move in a certain way. Alright? So parang siya yung molecular kinetic energy. So yun yung mag-apply ka ng heat, may excite yung mga molecules at that particular point and they will move. And then here we are assuming that these molecules, dahil nasa very thin rod lang tayo, they can only move to the left or to the right. Baliktad pala. To the right or to the left. Right? So yung mga molecules dito, pag pinainitan ko yan, may excite sila. Mafo-force sila na gumalaw. And our assumption ay pwede lang siyang gumalaw from the left to the right. And then yun nandito naman to the left. So left or right lang yung paggalaw ng mga molecules. But there are lots of molecules within this space. So pag nagtama sila, meron ka molecule dito, molecule dyan, nagtama sila in time, madideflect sila, and then that will cause movements or vibrations in the molecular level. So the more molecular activity, the more vibrations caused by the collision of molecules, yun yung nangyayaring heat. Right? So kaya ito yung ginawa ni Siltanen. Dun sa section 2.1 niya, minodel niya yung probabilistic nature ng pagtatama ng mga heat molecules. Right? So sino dito mga nag 1A2 na? Math 1A2, stochastic processes. Pero ang problema ko pala, pinayagan ko yung mga bagong junior lang no, na mag-take. So probably you haven't taken 1A2 yet. Kaya i-skip ko sana yung kaya i-skip ko yung kay Siltanen na section 2.1 kasi he discussed the derivation of the heat equation using Brownian motion. Pero yung Brownian motion, it's a stochastic process. And stochastic processes ay dinidiscuss pa lang sa Math 1A2. And I guess hindi siya required sa BS Math students, ano? So, sa applied math lang siya required. Pero tinake ko siya kasing elective no undergrad. So, bakit nga ba? Nagsisi ako kasi mahirap yung subject. Pero essentially, ganun yung ginawa. Minodel niya yung probability of two molecules hitting each other. Okay? Kasi doon nakadepende yung pagpropagate ng molecular kinetic energy. And the higher the molecular kinetic energy is, the higher the temperature. Okay? So basically, yun yung nangyayari. Nagkakaroon ka ng heat kasi nagtatama or nagko-collide yung mga molecules. Yun yung itatry natin na i-model dito. Okay? And siguro I'll introduce na rin one technical term. Instead of heat flow or heat diffusion, maybe we can call it heat flux. Okay? Para mukhang matalino, right? So yung flux parang fancy term lang for flow. And this is basically how temperature will flow from one place to another. Okay? And I think that will complete the picture, at least from a qualitative or from a physical point of view. The rate at which the temperature change at a particular temporal and spatial variable or value of those variables is actually influenced or can be quantified by looking at how heat flow within the material and what are the heat sources. Okay, so in essence, we will try to make it more mathematical now. So ganito yung ginagawa ng mga physicists, ano, kaya magaling din sila dapat sa math. Kasi gagawa sila ng observation about the real world. And then, sulat nila yan na ganyan. And then, susunod nilang step ay, paano ko siya mako-quantify mathematically? Or paano ko siya masusulat mathematically? How do I quantize or quantify these objects, right? So if I will let U to be the temperature, the left-hand side is easy. Because the left-hand side will just be the rate at which the temperature changes, right? So kung ang temperature variable ko ay UXT, okay? Tapos titingnan ko lang yung dynamics niya in time, okay? Kasi rito at a particular time, ang tinitingnan ko. So ito ay derivative lamang with respect to the time variable, okay? Because this is the rate at which the temperature changes at a particular point x, t with respect to time. Kasi titingnan ko yung evolution. nung pagbabago ng temperature. Dito sa left-hand side, kinukuha ko yung influence ng temporal variable. Dito sa right-hand side, titingnan natin ano yung behavior with respect to the spatial variables. Okay? Tapos siguro isingit ko na rin yung sinabi ni Victor kanina, nakadepende daw sa material properties. So basically, what are the material properties? Siguro meron siya rito specific heat depending on depending on the material. Tandaan niyo ba kung ano yung specific heat? The specific heat, I guess, if I remember it right, you can correct me if I'm wrong. Ayoko rin kasi ng physics. Pero yung specific heat, siya yung amount of energy needed para ma-raise by 1 degree yung temperature. And that depends on the material itself. Tapos aside from the specific heat, ano pa ba? Siguro yung ano rin, yung yung density nung material. So let's call the density rho. Okay. So nandun din, gaano ka dense yung material. Kasi the denser the material is, the easier the heat flow will be, or the easier for kinetic energy to propagate. Kasi kung dense siya, magkakadikit yung mga molecules, ibig sabihin konting galaw lang ng isang molecule, maapektuhan niya yung kabilang molecule. Alright? Hindi katulad sa air. Sa air na magkakalayo yung molecules, mas maraming energy yung kailangan mo para magbanggaan sila kasi magkakalayo nga sila. Alright? And there could be some other material properties that can affect the rate at which the temperature change with respect to time. Siguro i-account na lang natin siya kasama nung S. So si S, nandiyan na yung specific heat, nandiyan na kung yung conduction or what? Conduction or insulation factors, etc. So lagay natin siya dyan. Okay. So yan yung rate at which the temperature change. Ngayon, itatry natin i-model yung right-hand side. Well, heat source. So tawagin na lang natin yung heat source to be a function Q of, say, time and space. Okay. So si capital Q, siya yung magko-quantify ng heat source, ng external heat source. Dun sa mga nag-ODE dyan, pwede natin itong i-consider as the forcing term. Okay? So ibig sabihin, ano yung external heat na nilalagay natin dun sa ating system? So tawagin natin siyang capital Q. Now, ang kailangan nating i-model ay kung paano nag-flow yung heat within the object. Ito yung medyo mahirap. Ito yung mas mahirap i-quantify. And for now, I will call it negative partial of a function q, little q, with respect to x. Okay. And q is basically what we call the heat flux. Okay, siya yung function na nagde-determine ng heat flux, all right? Or how heat flow from one point to another. Yun yung siya si little q, right? Tapos tingnan natin paano natin mako-quantify si little q, right? Or yung derivative ni little q with respect to the variable x. Okay? So tingnan natin, so para makuha yung pagmamodel kay little q, kailangan ko ngayon mag-zoom in doon sa thin wire or doon sa thin rod. Okay? So halimbawa, sorry hindi ako magaling mag-drawing, so pagpasensyahan nyo na. Okay. Tingnan natin ano yung mangyayari on a particular point x and another point x plus delta x na malapit kay x. So ito yung portion ng ating thin rod. Tawagin ko nasa x tayo. Tapos pupunta tayo sa x plus delta x. Okay? Tapos titingnan natin paano nagfa-flow yung heat from x to x plus delta x. So you have here heat flowing in that direction. Tapos meron din kang papalabas na heat. Right? So basically, you have heat coming in, galing dun sa kaliwa, tapos magfa-flow siya papunta dun sa kanan, x plus delta x, which will eventually escape from the interior mula dun sa interval x, x plus delta x. So you can think of this flux. So yung yung arrow na yan, siya yung flux o yung flow. Ito ay incoming heat, papasok dun sa ating system. Tapos ito naman, ito yung papalabas ng ating system. Okay? So si Q of xt, sabi ko kanina, si Q or the heat flux is a function of x and t, which will represent the heat flow from left to right. Okay? So ibig sabihin dito, gusto ko makita kung paano nag-change yung heat with respect to the location x in space. Okay? So basically, kailangan kong malaman kung ano yung Q of, kailangan kong malaman yung change in what? Gusto ko malaman yung change in the temperature. Okay? Gusto ko malaman yung um, yung pagbabago ng heat which affects the temperature from point X to point X plus delta X. Alright? So kung titingnan natin yan, paano ko malalaman yung, or paano ko, actually madali lang pala to. Inisip ko kung paano ko siya ipuput into a question eh. Gusto ko malaman ngayon ano yung dx dq. Alright? Ano tong value na to? Actually, by definition, madali lang siya, no? Kasi kailangan ko lang kunin, this is the rate or the instantaneous rate at which Q changes with respect to change in X. So basically, kukunin ko lamang yung function value ng flux sa X plus delta X. Right? How much energy is coming out or how much heat is coming out of X plus delta X. Okay? So, ang value nun ay Q of X plus delta X lamang. Kasi nga si Q, siya yung nagre-represent ng heat flux from left to right. So, ibig sabihin, kunin ko lang yung function value niya at the point X plus delta X. Tapos para malaman ko yung rate at which the flux changes with respect to the spatial variable X, ma-minus ko lang dito yung Q of X. Tapos i-divide ko lang to by delta X to get the relative change in the flux. Kasi nakadepende yung change in flux dun sa distance traveled by the molecule. Alright? Tapos gusto ko tong gawin for a very, very small amount or very, very small value of x. So basically, kukunin ko yung limit ng both sides with respect to delta x approaching 0. Okay? And then you all know that this is equal to the derivative of q. Ay kaya lang si q nga pala ay space and time is dependent on space and time. So dapat ito ay may comma t. Tapos ito ay may comma t. So basically, this is just the partial of q with respect to x. All right? Which is basically fine because yun yung hinahanap natin dito sa right-hand side na yan. Pero why the negative sign? Hold on. Double check ko nga yung mga sign ko. Parang may mali akong sign. Okay? Yeah, I think this is fine so far, right? Pero bakit nag-introduce dito ng negative sign? Kasi anong mangyari? Kailan nagiging positive tong dq over dx? Sige. Kailan nagiging positive si dq over dx? Dalawa lang naman yung scenarios, no? Sa dalawa lang nakadepende si partial ni q with respect to x. Nakadepende siya lang kay q at x plus delta x at saka kay q of x. Kailan positive itong ratio na ito? Assuming that delta x is positive. Kailangan careful ako sa signs eh. Okay, do you agree that dq over dx will be positive if q of x plus delta x is positive, is larger than q of x, right? So magiging positive yung quotient kapag ka positive yung numerator. Pero yung numerator is the flux at x plus delta x comma t minus q of x comma t, right? So ibig sabihin magiging positive si dq over dx kapag ka mas malaki yung flux dito kaysa sa flux na nandito. Okay? Pero, ano yung effect niya sa temperature? So kung mas malaki yung flux dito, so ibig sabihin mas malaki yung heat na lumalabas doon sa ating interval of interest kaysa doon sa heat na pumapasok, right? Because we are analyzing when this quantity will be greater than zero. Okay? And again, it will be greater than zero if the outgoing flux is larger than the incoming flux. Mas malaking temperature na lumalabas kaysa dun sa temperature na pumapasok. Okay? So, pero anong effect niya, hindi pala temperature, dun sa heat na pumapasok at lumalabas. Pero kapag mas malaki yung flux na lumalabas, ano yung nangyayari sa temperature? Tumataas ba yung temperature dito or lumili? Again, our analysis is there is more heat coming out than heat that is coming in. Kasi mas malaki yung Q of X plus delta X kaysa dun sa Q of X. Mas maraming lumalabas kaysa dun sa pumapasok. So, and then Victor and Neo are right. Tama, bumababa yung temperature dito. Kaya naman, ang gusto natin ay yung negative. Okay? Kasi ibig sabihin, dun tayo nag-i-introduce ng heat. Okay? Mas umiinit siya kapag mas malaki yung pumapasok na heat energy kaysa dun sa lumalabas. That's why there is a negative sign in here. Kasi yun yung net effect niya dun sa temperature. Okay? Now, the problem here is, okay, sorry, okay na pala kasi lagyan mo lang yan ng negative sign, makukuha na natin yung negative partial ni Q with respect to X. Ito lang yung quantity na yan. Kaya lang ang problema, hindi siya magandang PDE. Kasi ang gusto natin, yung model natin para dun sa heat flow ay nakadepende lang kay U at saka sa mga derivatives niya. So basically, walang masyadong panggamit yung function Q dito sa equation natin. Kailangan mawala si little q. Kasi gusto ko lahat ng derivatives ay with respect lahat ng derivatives na involved ay derivative lamang ni temperature. But Q again is the heat flux. Siya yung nagsasabi ng pag-flow ng heat. Kaya lang extra variable na siya. So, nasa loob siya ng derivative. So, we cannot keep little q in our model. We can keep capital Q, yung heat source term, kasi si Q, hindi naman siya dinidifferentiate. Okay? So, kaya pwede siyang maging forcing term. Si S at saka si rho, pwede siyang nandyan kasi siya ay material composition. Pero hindi magandang meron ka pang variable Q dito sa right-hand side ng equation. Gusto natin, if possible, lahat ng variable lang na dinidifferentiate ay function U or dependent variable U. So kailangan ko kayong i-model ano si Q in terms of U. Remember, Q is the heat flux. Paano nagta-travel yung heat? Pero gusto ko siyang express in terms of the temperature. How can we write the model down? Well, dun sa book ni Siltanen, the heat flow, the partial Q with respect to X, or the function Q, is actually modeled using statistical thermodynamics or probabilistic thermodynamics. Doon niya ginamit yung Brownian motion kung paano niya na-quantify yung partial ni Q with respect to X. Kaya lang, wala tayong time para i-discuss yung Brownian motion, at ayoko mag-stochastic analysis dito. So gagawin natin yung mas simpleng observation. And we will go back to the time of Fourier. So, si Fourier, siya yung naka-observe o siya yung nag-formalize ng mga sumusunod na observation about heat flow. And the genius of Fourier led to a law that represents ano si Q in terms of the temperature, okay? Or how the heat flux can be written in terms of the temperature U. Okay? Na-verify naman later ng mga experimental physicists through statistical thermodynamics. O yun nga, yung probabilistic thermodynamics na kailangan niya ng Brownian motion. Pero luckily, napansin ni Fourier ang mga sumusunod na bagay. Una, ano yung nangyayari kapag walang heat flow? So kapag walang heat flow, ibig sabihin ay what? Kapag walang heat flow, ibig sabihin yung flux mo ay equal kay 0. So, kailan to nangyayari? Kapag ang heat flux mo ay equal kay 0. Or ano mangyayari kapag si Q ay 0? Kapag yung heat flux mo ay 0, ibig sabihin walang walang heat na pumapasok at wala ring heat na lumalabas. If Q is 0 all throughout the rod, then that means there's no heat coming in nor heat coming out. Okay? So ibig sabihin yung temperature dito sa loob ng rod ay constant. Okay? So yun yung sinasabi ni Fourier. So if I will design a function that will represent that will explicitly relate heat flow with temperature, dapat yung model na yon should satisfy the following condition. Na kapag wala kang heat flux, kapag si Q ay equal kay 0, dapat yung temperature mo ay constant. Or it also goes both ways. So dun sa model na gagawin ko that will relate the heat flux Q and the temperature function U, dapat masasatisfy niya to. Na kapag constant function si U, dapat yung heat flux ay 0. Okay? Kasi nire-represent nito kapag 0 si Q, ibig sabihin walang heat flow within the segment of the rod. Ibig sabihin walang pagbabago dun sa temperature. That means that the temperature will be constant. Okay? So kailangan natin itong i-guarantee pag nagawa na tayo ng equation involving Q and U. Right? Next observation by Fourier. Sabi niya, the heat flux is positive. Pero I think nasabi na natin to kanina, no? From higher temperature to lower temperature. So sabi niya, pag meron kang isang point dito at isang point dito, okay? Kung mas mataas yung temperature dito sa side na to, ibig sabihin magmo-move yung molecule, so magta-travel yung heat coming from something with a higher temperature papunta sa something with a lower temperature. Okay? Kaya nga halimbawa ito yung principle behind induction cookers, ano? So pwede kang may induction cooker ka, tapos mag-apply ka ng heat source kasi alam natin na nagto-travel yung heat mula sa isang heat source. Ibig sabihin meron kang high temperature papunta sa isang point in space with a lower temperature. Okay? And if that is the case, then magiging positive yung heat flux. Right? So kung meron kang movement from high temperature to a lower temperature, so ibig sabihin dapat positive si heat flux. Because that means you have more energy coming in than energy coming out. So kaya dapat positive yung value ni Q. And then the last observation that Fourier made is that heat flow is proportional to the change in the temperature. Or sorry, heat flux is proportional to the change in temperature. To the change in temperature. Okay. So ibig sabihin pag mas malaki yung change in the temperature, mas malaking heat yung nagflow, which makes sense, right? Parang sabihin niyo, sir, parang obvious na obvious yung mga pinagsasabi mo. Yes, kasi parang may notion tayo na parehas lang yung heat sa temperature, ano? But on a physical point of view, yung heat siya yung behavior or collision ng mga molecules. And temperature is simply the effect of that collision between molecules. Okay? Kaya meron tayong observation, ito number 3, na yung heat flow o yung heat flux is proportional to the change in temperature. Meaning pag malaki yung change in temperature, ibig sabihin mas malaki yung nangyaring flow of heat energy from one source to another. So mas maraming energy yung na-consume because more molecules collided, and that collision or that more collision between molecules produced higher temperatures. So ito yung mga na-observe ni Fourier. And he synthesized these three observations into a governing equation. Sabi ni Fourier, ito yung nakuha ko sa tatlong physical observations na yan. Sabi niya, yung heat flux, little q of xt, ay equal lamang sa negative, so ko siyang gawing constant. Okay, tawagin ko na lang negative d times du over dx. Sabi niya, yung proportion, yung heat flux ay equal sa negative d of du over dx. At the amazing thing about this ay nakuha niya lang yon mula dito sa tatlong observations na yan. Okay? And this equation here is actually what is called the Fourier law of heat diffusion or heat conduction, which is later verified by experimental physicists, or yung mga nag-aaral ng statistical thermodynamics. Na oo nga, no, tama si Fourier. Way back kailan ba nabuhay si Fourier? 16 or 17 or 1800, sometime around, or 1900s na ba si Fourier? 19th century na yata siya. But anyway, these are hundreds of years ago na ngayon natin na-verify using some sophisticated techniques. But people like Fourier, the visionaries they are, meron lang siyang tatlong observations na sabi niya, therefore, Q of xt ay equals sa negative d ng du over dx. Now, let's verify. Tama ba si Fourier nung sinabi niya yan? Verify natin na yung tatlong observations niya ay na-encapsulate into this nice equation here, relating the heat flux and the temperature U. Okay, una, sabi niya, kapag ka walang heat flow, that means dapat kapag ka si Q ay 0, ibig sabihin dapat constant yung temperature. And vice versa, kapag ka constant yung temperature dun sa object mo, ibig sabihin walang flow ng energy. O yung net flow ng energy ay equal kay 0. Okay? Tingnan natin kung nandun siya sa model. Well, when temperature is a constant, it doesn't change all throughout your rod. Ibig sabihin si u ay constant. The partial derivative of u with respect to x will be 0. So the right-hand side will be 0, q of t siya. So indeed, kapag ka si u ay constant function, ang heat flux ay equal kay 0, yes, condition number 1 or observation number 1 of Fourier is satisfied. Okay, next condition, heat flux is positive from higher temperature to lower temperature. So ibig sabihin kung ang du over dx ay positive, ibig sabihin nagkaroon tayo ng increase in temperature. So pag nagkaroon tayo ng increase in temperature, okay? Tapos here I'm assuming D is positive. Okay. Tingnan natin kung magme-make sense siya. So when there is an increase in temperature, that means du over dx is positive. D is positive, so the flux is negative. So pag tumataas yung temperature, dapat negative yung flux. Does that make sense? Tama ba? Kapag tumaas yung temperature, pag tumaas yung temperature, ibig sabihin du over dx is positive. Meaning from one point to another, tumaas yung temperature, so yung derivative ni u with respect to x ay positive. So there is an increase in temperature. Increase in temperature. Tapos times d, which is positive, times a negative sign. So basically, yung flux daw ay negative. So question, is the flux negative when there is an increase in temperature? When there is an increase in temperature. Does it physically make sense? Kasi yun yung sinasabi ng Fourier law. Pero nag-agree ba siya doon sa observation niya? Specifically, observation number 2. Copy-paste ko lang to. Copy. Tapos paste ko siya dito. Tingnan natin kung mag-make sense siya dun sa condition na yan. Wala siyang boundary. Okay. So, eto ba can be translated to this statement? So, sabi niya, ang flux daw ay, sabi ng Fourier law, ang flux daw ay negative kapag ka merong increase sa temperature. Can we reconcile that with the fact na sinabi natin kanina, heat flux is positive from higher temperature to lower temperature? Tama naman, no? Baligtad lang yung aking statement. Kasi kapag ka may increase in temperature, ibig sabihin mas mataas yung coming in, yung flux coming in, kesa dun sa flux coming out. Or dun sa heat coming in, meron ka kasing increase in temperature, no? Lumalaki yung temperature kapag ka mas malaki yung heat na pumapasok kesa dun sa heat na lumalabas. So that means the flux will be greater here than the flux here. So ibig sabihin, si Q ay magiging negative. Kasi mas malaki yung coming in kesa dun sa coming out. And vice versa. Where heat flux will be positive from higher temperature to lower temperature. So ibig sabihin si heat flux daw ay positive kapag ka nagmo-move tayo from high temperature to lower temperature. So ibig sabihin si du over dx ay negative. Nag-stuck ba yung screen ko or okay pa naman? Nag-stuck kasi siya sa monitor ko. So I don't know if I'm still in the meeting or not. Paramdam nga kayo, guys. Okay, how about the screen? Nag-move na ba yung screen ko? Nandun na ba ako uli sa dun sa Fourier law of heat conduction? Okay. So sa akin lang hindi nag-update. So anyway, yeah. I-verify natin. Sabi natin dun sa ayan, nag-update na siya. Sabi natin sa observation ni Fourier kanina, heat flux is positive from higher to lower temperature. So heat flux is positive from higher to lower temperature. Pero pag nag-start tayo from higher to lower temperature, so higher to lower temperature, so ibig sabihin nag-decrease yung temperature. Nag-decrease yung temperature, so ibig sabihin ang du over dx ay negative. Times negative, so that's positive. Times a positive number, that's positive. Heat flux is positive, agreeing with his second observation. Okay? So, ayos. Maganda yung analysis ni Fourier. Last thing to analyze is, sabi ni Fourier dun sa observation niya, heat flux is proportional to the change in temperature. And that is basically the embodiment of this statement. Si heat flux ay proportional, so meron kang proportionality constant dun sa change in temperature, which is du over dx. Okay? Parang galing-galing, no? Meron lang tatlong physical observations si Fourier, tapos nakakuha na siya ng isang equation coming from those three statements. Sabi niya, and that is what we call the Fourier law of thermodynamics. Sabi niya, ang heat flux Q ay equals to negative d times du over dx. And actually, this is what I want. Because remember, in our quantification of the heat propagation earlier, sabi lang natin ay ito. Ito yung magiging model natin para sa heat flow. Copy paste ko lang siya sa baba. Okay? Sabi ko kanina, ang problema natin dito, itong derivative na to. Ayoko na ng isa pang function na involved sa derivative na yan. Okay? Now, yes. So the problem there would just be, kailangan ko itong ma-express in terms of the temperature. Pero na-discover na yan ni Fourier. Sabi ni Fourier, yeah, ang Q of xt ay equals to negative d over du over dx. Okay? Now, let's factor everything into this model that we have. Okay? Pwede ko pa pala itong i-simplify ng kaunti, ano? Kasi si S ay yung specific heat, o nandito na sama-sama yung mga properties ng material. Tapos yung density ay nandito na rin. But we can safely assume that in a physical environment, these two properties doesn't change through time. And now, meron kang copper, yung specific heat ng copper, hindi naman nagbabago through time. Unless radioactive yung material, pero ang copper ay hindi naman radioactive. Pero it's safe to assume that S is independent of time. Kaya nga S of X lang yung nilagay ko. Also, the density is also constant with respect to time. So itong S of X at saka rho of X, pwede siyang lumabas ng time derivative dito. So the right-hand side will just be the function s times rho times the derivative of t, the derivative of u with respect to time. So okay na yan. And then alam na natin na itong right-hand side, negative dq over dx, pero alam na natin kung saan equals si q. Si q ay equals sa negative d times du over dx. So I'll replace the q here by negative d over dx. So maging negative partial ng q with respect to x, but q is the negative d times change in temperature plus the heat source. Okay? And then I'll simplify. D is negative d is a constant, so this will come out of the derivative. So matitira na lamang ay positive d. Then you have a partial with respect to x and another partial with respect to x of the variable or of the dependent variable u. So this will just be the second derivative of u with respect to the spatial variable x plus q of xt. Okay, duplicate. Okay, there we go. Tapos ang dami pang mga functions dito, pero pwede akong mag-throw in ng mga sumusunod na assumptions, okay? Na assumptions that we will just throw in for the sake of simplicity. All right? Kasi gusto natin mas specific or mas madali muna yung i-consider natin na problem. So it's a first order model really, right? Or a zeroth level model muna. So here we will assume that S and rho are constants. Okay. So kunwari yung specific heat, hindi siya nagba-vary kung nasa ang part naman ako ng rod. So parang magiging i-consider natin na homogeneous yung rod. So yung specific heat na nandito sa position X na to ay parehas dun sa specific heat dito sa position na to, sa X value na to. And the same thing as density. Yung density ng material dito ay kaparehas lang ng density sa material dun sa point na yon. So ibig sabihin homogeneous yung material. Hindi nagbabago yung material composition. Uniform yung material all throughout. So these two guys can be treated as constants, or we can put the assumption that they are constants. Kasi napaka-komplikado na ng solution kapag ka function pa rin sila ni X. And then we can also assume for now that there are no heat sources. And there are no external heat sources. So ibig sabihin, ang heat source na lang natin ay manggagaling dun sa boundary condition. So i-assume natin na at the boundaries, x equals 0 and x equals capital L, meron ng ambient temperature dun sa dalawang boundaries na yun. So meron ka ng temperature dito sa point, meron ka ng temperature dito, meron ka ng temperature dito, sila yung mga boundary conditions. Tapos meron ka na ring initial condition. What is the temperature all throughout the rod at T equals 0? So yun yung ina-assume natin. Meron na tayong boundary conditions, meaning the temperature on the boundaries at all time values. So alam natin si U of 0, T, at saka si U of L, T. Alam ko yung function of time na magsasabi sa akin ano yung temperature dun sa dalawang boundaries. Kaya ang tawag sa kanya ay boundary conditions. Kasi alam natin kung ano yung temperature sa lahat ng time values dun sa boundaries ng ating physical domain. Okay? Tapos alam ko rin kung ano yung initial condition. Yung initial condition naman, siya yung temperature all throughout the, siya yung temperature all throughout the rod. So alam ko yung temperature sa buong rod sa kahit anong x na nandun sa interval 0 to L at the starting time. 0, at T equals 0. Kaya ang tawag sa kanya initial condition. Kasi alam natin ano yung temperature doon sa buong rod when T is equal to 0. And other than that, we will assume that there are no heat sources all throughout the time experiment. Wala nang external heat na makakaapekto dun sa system. aside from those that were already in the system at time t equals 0 and at the boundaries when x is equal to 0 and x equals L. Wala nang nadadagdag na heat. So walang aircon. So ano tayo, old school. Walang aircon dun sa problem. So that means we are assuming that Q is equal to 0. Okay? So that means mas simple na yung model natin. So we have a partial derivative of U with respect to t. X is a function of x and t equals d times partial of u with respect to x 2 times. So ito yung heat equation nating tinatawag, right? So ito yung one-dimensional heat equation na tinatawag ding Laplace equation. Denmark and Jeff, they worked on the heat equation during the mid-year. Pero ano yan, steady state yung ginawa nila. Ibig sabihin, hindi na nagbabago yung temperature through time. Tama ba, Denmark, no? Ganun yung kinonsider nyo. Hindi nagbabago yung temperature with respect to time kasi ina-assume natin na siya ay steady heat equation or steady time heat equation. So, hindi siya nagbabago with respect to time. So, 0 yung derivative ni u with respect to t. So, second derivative lang equals 0. Yung kinonsider niya. Yun yung Laplacian equation. Dito pwede natin isama ano yung mangyari all throughout time. And this is the heat equation or the one-dimensional heat equation. Okay. Tapos, isosolve nyo itong PDE na to. So, pag nasolve mo itong PDE na to, you solve for u, malalaman mo yung general solution. Ano yung function u in terms of x and t. Alright? Pero hindi unique yung magiging solution pag sinolve mo to using techniques in PDE and ODE. So, kailangan nating ilagay ano yung boundary condition. So, yung boundary condition, dapat alam natin yung function u that depends only on the time. So, ibig sabihin, dapat alam ko yung temperature sa x equals 0 at all times. Ito yung boundary condition. Tawagin natin itong g of t. Okay? Ito yung function of time na nagsasabi ano yung temperature dun sa left endpoint at all time values. Tapos kailangan alam din natin yung value ng temperature at the right boundary at all times. Tawagin natin itong function h. Okay. And these two are functions of positive values of t. Tapos ito yung tinatawag natin na boundary conditions. So ibig sabihin, monitor natin yung temperature dun sa magkabilang dulo ng rod at all times t. Okay? And then, dapat meron tayong initial condition. Yung initial condition natin ay temperature at all points in the rod at time 0. Tawagin natin itong f of x, where x is within the interval 0 to L. So ito naman yung initial condition. Okay. If you're dealing with a forward problem, so ito yung governing law dun sa ating heat propagation problem or the heat diffusion problem. This is the governing law, which basically we derive from Fourier's principle of or Fourier's law of heat conduction. Okay, ito yung governing law. Tapos pag alam mo yung inputs dun sa system, meaning alam mo yung boundary conditions, ano yung boundaries dun sa magkabilang dulo ng rod, at alam mo yung initial condition, what is the temperature profile in all throughout the rod at time t equals 0, okay? Yun yung initial condition, right? Ito yung tatlong inputs, ito yung governing law, makukuha mo yung output. Ang output natin ay function u of x comma t. Yun yung pag-solve ng forward problem. So you'll get a function of the space and temporal variables na magsasabi sa'yo ano yung temperature at a point x in the rod at any time t from 0 to positive infinity. So yun yung forward problem. Now, the inverse problem can be phrased as either looking for the boundary conditions and or the initial conditions para may masatisfy tayo na heat profile. Yun yung inverse problem. Gusto mong makontrol yung temperature sa buong rod at all times. So kailangan meron tayong gustong function u to be the solution of this heat equation. The problem is what should be the boundary conditions and the initial conditions. Yun yung inverse problem. Kasi hinahanap natin yung appropriate inputs para makuha yung desired output natin na temperature profile. Okay? Or as I've mentioned kanina, pwede nating tingnan kung ano yung pwede nating tingnan as output ay yung temperature in the entire rod at the time capital T. Tapos ang gusto nating makita, ano yung nangyari prior to the time capital T. So what was the temperature all throughout the rod at times little t prior to the terminal time capital T. Right? Pero later natin yung pupuntahan, siguro I'll start next meeting by showing one particular example of the solution to the heat equation. All right? So kasi halimbawa, ano yung gagawin ko sanang example? Let me see. I think I wrote it somewhere. Kasi hindi ko sa ulo yung solution. Pero nawala na. Hindi ko na yeah, there we go. Yeah. So ito yung example na binigay ni Siltanen. And probably you can ponder about this. Siguro gawin kong isang homework. Anong homework na tayo? I forgot yung homework number natin. Pero anyway, please verify. So verify. Pero isi-send ko rin ito mamaya sa Canvas. Verify that this function, u of xt equals teka, mali yung hindi ko na-copy yung solution. Hold on, guys. Okay, there you go. Okay. Show that or verify that u of xt equals 10 e to the negative 4t sine 2x is the solution to the following heat equation. So ito yung heat equation na sinusolve daw niyan. Partial of u with respect to t, of course, in governing law, equals negative partial ng u with respect to x. So that means here, positive to dapat. Tama ba? Yeah. I-consider ko lang na si constant d ay equal kay 1. So ito ay magiging second partial of x with respect to, of u with respect to x. So ibig sabihin, simple lang to. D is equal to 1. And then, ang kanyang boundary conditions ay u of 0t. And yung u of lt ay parehas equal kay 0 for all t equals 0. So that means yung dalawang endpoints, laging 0 yung temperature nila. So nandito ka sa rod na to, yung data natin ay ito. Dito sa point na to, at saka sa point na to, all throughout the time domain, laging 0 yung temperature. So meron kang 0 temperature dun sa boundaries. So yan yung sinasabi ng boundary condition natin. Laging 0 yung temperature dun sa magkabilang dulo ng rod. Tapos ang initial condition ay ito. U of x0 ay equal kay 10 sine 2x. So ito naman yung tinatawag natin na initial condition. So ibig sabihin, at time t equals 0, sa unang-unang panahon or at the beginning of this experiment, yung temperature dito sa isang point x na to ay given by 10 times sine of 2x. Okay. Bigyan ko pala ng 0 to L to. No? Dapat si x ay element ng 0 to pi. So ang length ng ating rod ay pi units. So nagsimula tayo sa x equals 0 at saka x equals pi. So ibig sabihin dito, ang capital L ko ay pi. So ito na yan. So pakita nyo lang na solution ng forward problem, yung u of xt equals 10 to the negative 40 times sine of 2x. Meaning this is the output when we know the following inputs. we know that the temperature at the boundaries is always equal to 0, and the temperature at the initial time is 10 sine of 2x. Of course, kung hindi pa kayo nakapag-PDE or hindi pa nakapag-ODE, hindi nyo malalaman or hindi kayo marunong kung paano isolve to in a forward sense, right? Hindi nyo to masosolve by hand kung wala pa kayong 152, right? Pero dahil given naman yung solution, kailangan nyo lang i-verify na siya talaga ay solution. Okay? So meaning, pag nag-plug in ba ako rito ng T equals, kapag ka yung U sa governing principle ay pinalitan ko ng 10 e to the negative 40 times sine 2x, magiging totoo ba tong equation na to? So you need to take the partial of U, the partial of this guy, with respect to time, at i-compare nyo siya sa second partial derivative of the same guy, pero with respect to x. Kasi sabi ng governing principle, dapat equal silang dalawa. Okay? Tapos, madali namang i-verify yung initial conditions saka yung boundary conditions. Kasi para makuha yung initial condition, dapat ang t ay equal kay 0. But when t is equal to 0, look at u. Right? Si t ay magzi-0, so yung exponent nito ay 0, e to the 0 ay 1, so meron lang tayong 10 sine 2x, which is the initial condition. Ayan, ginawa ko na yung isang verification for you. And then, kapag ka si x ay 0, okay, pagka si x 0, sine ay 0, sine niya ay 0, so magzi-0 pa rin yan. Tapos kapag ka si x ay pi, pag si x ay pi, so magiging sine of 2 pi is 0, this guy is 0, so that's fine. Boundary conditions is satisfied. So the only thing that you need to look at is, tama ba? Nasa-satisfy ba niya yung heat equation? Sorry. Yeah, and this is an example of a harmonic function. Harmonic function siya kasi siya ay solution ng Laplace equation. Okay? And yeah, I think I'll stop here. Sorry, overtime na pala ako, 11:35. Sorry, hindi ko napansin. Pero that will be your, hindi ko tanda kung pang ilang homework na. Pero isasendan ko kayo ng typewritten na questionnaire dito. Tapos sabihin ko yung deadline. Kailan nyo gustong i-deadline? Will be 1 week enough? So sa October 20 yung deadline for this homework. Pero actually, madali lang siya, no? Magpa-partial lang kayo. At dapat marunong na kayo mag-partial kasi math ano lang to, di ba? Math 38 lang. Okay? So we'll end here. Any questions? Okay, so I hope you got something new here. Ito yung kagandahan sa 191 eh. Wala tayong outline na sinusunod. So we can be as relaxed as we want, ano? And we can tackle anything under the sun technically. So kaya medyo interesting kasi yung heat equation eh. At madali siyang i-discuss, madali siyang i-laymanize, okay? Tapos practical yung application niya. So merong motivational part that even a layman can appreciate, okay? So any questions, pahabol? Okay, so kung wala na, so just watch out for the submission bin for this. Okay, may suggestion si Daryl, sabay na lang daw natin sa problem set 1.1. Okay, that's fine. So gawin nating deadline ay October 21, 11:59 p.m. Pero individual lang naman to. Okay, so that's fine. And then, but if you can submit ahead of time, kindly do so kasi ano lang naman siya eh, low-hanging fruit lang naman to. Madali lang siyang gawin, so you can submit as early as you want para wala na kayong isipin next week, right? But the deadliest deadline is on October 21, 11:59 p.m. Okay? So, okay, with that, I think we can call it a day. So thank you guys for joining me today, this morning. And yeah, happy weekend na pala kasi sa Tuesday na ulit tayo magkikita-kita. All right? Bye guys and keep safe. Thank you.